If you are watching this video, it is because you do not have Flash or a Flash emulator on your computer, and we're going to be doing this worksheet together through this video, or at least I'll be showing you what the Flash thing is supposed to be. It says go to this website here, but you're not going to do that. You're going to just watch this video. It says this virtual animation will help you visualize what's happening during a chemical reaction and how various factors influence rate, which is how fast a reaction goes, which is what we're talking about this week. So what can we do to make a reaction go faster? What can we do to make it go slower? So it says the boxes on the right-hand side of the screen will say this, and so here they all say that except one of them got deleted, which was this one, 20. All right, so I click setup, and I got some green and blue circles here. So it says using these standard parameters, you'll observe how long it takes for all of the reactants to turn into products. So these are reactants. Okay? Click setup and some green and blue circles appear. I did that. Click start. And then it's asking what do the green and blue circles do once you click start. What do these green and blue circles represent? What happens when a green circle and a blue circle run into each other? And what do the red circles represent? And then it asks you to just let the animation run until all of the green and blue circles have combined and you have only red circles left. And how long does that take? And it says be patient because it does take a while. So let's run this and you can answer those questions while you watch. So when I hit start, you start to see some red circles appear. Now those red circles appear when a green circle and a blue circle run into each other, but not every time. So you'll be able to see this more later. So right there, I don't know if you saw that, but the blue and the green here ran into each other and they didn't turn red. And that's because not every chemical reaction has enough energy to react. So they have to bump into each other in the right orientation. Like the side that's looking for electron over here has to collide with the side that's looking for one over there. They have to find each other. You know, these molecules have to find each other. They have to run into each other. And when they do, they have to combine and have enough energy to react, and that's called activation energy. So now we're down to 3 greens and 3 blues, and we're going to run this out until they completely react with each other. So it might take a while, but when you watch them react, oh, these are going to collide. Oh, they're going to collide. Oh, and then they bounce. Did you see that? So that means that when they collided with each other, they did not have enough energy, enough activation energy. Oh, here we go. Head-on collision. That looks pretty good. Enough activation energy to react with each other. So not every collision produces a reaction. So we think about the molecules in a chemical reaction. They're in there. They're always moving. Molecules never stop moving unless the temperature is like absolute zero. Which does not actually occur. It's more like one of those theoretical things. But the molecules are always moving, even after they react. It's not like they react and turn red and then they're like, oh, freeze. They keep moving. And something about the simulation is they don't bounce off of each other, which is what they would do in real life. The only thing they bounce off of here. Ooh, let's see if they react right here. Oh, yep, down to just 1 green and 1 blue, and they have to find each other and they have to react. And they have to react with enough energy. And again, this can take a while, but these molecules are always moving. They also collide with each other. That's not really something that's being shown here. They kind of just pass through each other, but that's not what happens in real life. They actually do bump off of each other. The only thing they seem to be bumping off here is the walls. And through that, eventually they will collide with each other. Ooh, this looks like they might do it. Oh, oh, no, they missed. Oh, they finally collided. So there is our time. Let's stop. It was like 244. So 244 seconds in order for all of these molecules to react with each other. All right. So on to the next section. So this time we're going to vary the concentration. So concentration is like amount. So to increase the concentration is going to mean that there's more green and blue circles. So here it says you would need to change which two numbers, highlight them in green. So A refers to how many balls of A we have. So A is green. So this one refers to how many green balls there are. B refers to how many blue balls there are. Temperature refers to the temperature. Volume is how big the space is. So this is our volume, how big the square is. And then A size is how big those particles are. And then B size is how big the B particles are. So remember, A is green and B is blue. And then let's just say product size. So product size is how big the product ends up being. So what you're going to do on this paper is you're going to highlight the thing, you're going to change two numbers. The two numbers you're going to change here that are going to increase the concentration of the particles at the start. So it's going to give us more particles. It says highlight your numbers in the ones you wrote above and multiply them by 4 and type the new numbers into the correct boxes on the animation screen in the virtual lab, and then click setup and then click start. So the concentration is these numbers, A and B. So how many A's you have versus how many B's you have, because the space isn't changing. So let's change those, and we're going to multiply these by 4. So this becomes 80, and this becomes 80. And we click setup. So way more circles here. Okay, so these two numbers are the ones you should highlight and change. So we're going to run this with those new more blue and more green. Okay, so we don't have to run this all the way out. The point is not to see times because, you know, that doesn't really matter. The goal here is to be able to explain why this is happening. And it was a little glitchy there, and then it finally fixed itself. So now we're down to the end. It's 78 seconds. Remember, we went to 240 something, 244 the first time. So this is significantly faster so far. These last couple have to find each other, but it's faster because there's just more of them at the beginning. Now it'll get slower and slower over time, but the concentration at the beginning, the reaction is going to go faster because there's more of them. And now we're at 100 seconds and we're almost, done, and our reaction's almost finished. This is almost twice as fast here. So we don't have to run this out to the end. You just have to describe how it's different. So that's concentration. So the next one is temperature. So in order to increase the temperature, what numbers in the table would you need to change? Well, that's pretty obvious because it's temperature would need to change. So take your highlighted number and multiply it by 5. So I'm going to do a reset here, set these back to their original 20, change the temperature to 100, and then we're going to run that out, and you're looking for what's different. And why does this difference make the circles more likely to run into each other? All right, so let's run that out. All right, so it'd be better if it wasn't running so slow or kind of choppy here. But I assume that's probably because of the flash emulator. But if you could see these molecules in real time, you would see that you could probably tell, but they're moving a lot faster. And that's what temperature does, is it makes the molecules vibrate faster. That's what temperature is. Like at its core, when you're feeling something's hot, the reason that it feels hot is because the molecules inside are moving faster. That's what temperature is. If you feel something cold, the molecules are moving slower. So molecule speed is temperature. So these molecules having a higher temperature, they are going to move faster, and that is going to make them collide with each other more often because they're bouncing around faster and they're moving into each other a lot faster. And so again, this is almost done. We're at 79 seconds, so a lot faster than the first one that we ran, but we don't need to run it all the way out. All right, so that's temperature. And then next is the surface area. So in order to increase the surface area, what numbers in the table would you need to change? And the answer would be size. If we make the surface area larger, we're going to make the particles smaller. So when you think about a chemical reaction, if you have a solid and you're trying to react it, you can make that reaction go faster by crushing your solid. The smaller the particles, the faster the reaction will go. So, but the way we're going to like simulate size and surface area increasing, we're going to increase the surface area by increasing the size, which is actually the opposite of what you do in real life, but this is just a simulation and they don't have the option. What I'd want to do is I would want to take the particles that are already here and I would want to chop the same number of particles up into like 4 pieces. That would be increasing the surface area, but I don't have that option. So here I'm going to change the size, and we're actually going to increase the size, thus increasing the surface area kind of like metaphorically, even though we're not actually increasing the surface area, we're just making these bigger. So let's change these to 60. And I'm going to go ahead and start. No, sorry, run setup and then start. All right, so we increased the surface area, in quotes, by making these particles larger, which is kind of what surface area does. So if you cut something into smaller pieces, you give more surface area for a reaction to occur, which is what is being illustrated here. Bigger particles, more surface area. It's just on an atomic scale, the surface area is actually getting smaller. The smaller the particle, the more surface area. So this is simulation is a little bit confusing. But again, it does go a lot faster. Increase the surface area, increase the rate when we're down to our last 2. And so that went pretty fast there. And again, you don't need to, we don't need to run this all the way out to the end. You don't need a time there. So let me stop. So that was surface area. So we're increasing the size to like demonstrate surface area increase. All right, again, what's different and why does this difference result in green circles more likely to run into each other? Because there's more surface area available, so they're more likely to collide with each other. Set all the variables back to baseline. So I'm just gonna reload the page to do that. Now we're going to do pressure. So in order to change the pressure, what would we want to change here? And the answer is volume. If we change the volume, we change the pressure because volume pushes the molecules closer together. If we decrease the volume, we can increase the pressure. And so if we make the molecules hang out closer together, then they're more likely to collide with each other. So it says take your circled number and divide it by 4. So we're going to make this volume smaller. This is 20. This is now 100. Setup. See? Tiny. And now that they're in this tiny box, it's hard to escape each other. They're all crowded in there. And if it's hard to escape each other, you're more likely to run into each other. See how quickly those are reacting? So this only works for gases. So if I put liquid molecules in this box here, ooh, it's already done. If I put liquid molecules in this box here, nothing would happen. Pressure doesn't do anything for liquids because you can't compress them, and you can't compress solids either. Like if you take a solid and you squish it, you can't make it any smaller. That's the definition of a solid. But gases have a lot of empty space, and so they are compressible. This is why you can, get a tank of oxygen on your back and go scuba diving, because you can compress that gas into a smaller container. And so this pressure works for gases. All right, what's the difference again? And why would this difference be more likely to result in blue-green circles running into each other? So then for this last one, you can pick a variable of your choice, and actually we're going to change all of the variables to try and make the reaction the fastest. So what do we want to do to each kind of variable to make this go quicker? So for A, does it have any limits here? No. Okay. So what I want to do is I want to reload this, and I want to change all the things. So I want more A, more B. That increases the concentration. So let's make these both equal to 80 like we did before. So increase the concentration. Then I want to increase the temperature. Let's make this hotter. Not colder, hotter, so the molecules move faster. And then, assuming they're gases, I want to decrease the volume. Remember, if you, let's make it 200. If you change the pressure for a molecule that is not a gas, nothing happens. So let's pretend it's a gas. And then I want to increase the size, which represents surface area. So I want to increase the surface area, which actually in real life, remember, if you're increasing the surface area of a molecule, you're actually cutting it into smaller pieces. But this animation doesn't have any way of me simulating that. So we're increasing the surface area to demonstrate this. So we'll go with 60 on the size, 60, and then we leave product size alone because that's not really going to affect anything. Setup. That looks kind of crazy. All right, start. I want a super fast reaction. I can't even see any blues. I think it's just glitchy. It says the product's all done. Oh, there it is. Okay, yeah, just got glitchy for a second, but that was super fast. So those are all the things that we can, well, there's one more, but you can't simulate that with this activity, and that's adding what's called a catalyst. And a catalyst is a chemical that you can add that lowers the activation energy and it speeds up a reaction. Now, the cool thing about catalysts is you don't use them up in the reaction. So if you put in like 5 grams of catalyst, the reaction goes super fast and you get 5 grams of catalyst back. And we use these in our body all the time. They're called enzymes. And enzymes are catalysts inside our body. So if we, you start chewing a piece of bread, you have an enzyme in your saliva called amylase, and the amylase starts breaking down those long chain carbohydrates, those starches, into sugar, because that's what starch is made out of. It's just sugar, 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 all glued together. So you start that digestion process and you kick that off starting in your mouth. And a lot of your enzymes are for digestion, like you have proteases to break down protein and lipases to break down fat. And they just make reactions go faster, and you get to reuse them. So the amylase that's in your spit, once you use it to break down a starch into a sugar, you keep using it over and over and over again, and it stays there. And that saves you some energy because you don't have to keep making them. So that's the 5. We can change concentration, temperature, we can change pressure, which is represented by volume here. We can change surface area, and then we can also add a catalyst. So those are the ones you're going to learn about this week to make reactions go faster.